Okay, so welcome everyone for the fourth live session for the course Introduction to Semiconductor Devices. As you know, it is being taught by Professor N.K. Imani from IIT Hyderabad, and I am your official PMRF TA for conducting these live sessions. So, I am Samadhan Kamble. I am a PhD scholar at IIT Madras. I work in experimental high energy physics in collaboration with the CMS experiment at Large Hadron Collider CERN. So I think let's get started without further ado. So by now, as you all know, that the plans for these sessions is quite simple. In the first 10 to 12 minutes, I'll briefly discuss the review of the current week's lecture content that will give you a short refresher going forward to solving the problems. Then we'll move to the solving assignment problems from the previous course offerings. And also I include some of the competitive exams questions relevant to these particular courses, uh, this particular week's content. So needless to say that these problems are similar to your current assignments and also will be helpful in the end semester examinations. So yes, with this I think you can always stop me at any time and ask me questions if you have any doubt or any clarification you seek. So till now, is my voice clear? Shall we move to the review first?
Yes.
Okay.
Yes, sir.
Okay, so going to the summary of this week's lecture content. Uh, Prior to this coming to this week, up to the beginning of this week, we have been considering the properties of semiconductor materials, in which we calculated electron and hole concentrations in thermal equilibrium and also determined the position of the Fermi level. We then moved for the considering the non-equilibrium condition in which excess electrons and holes, which are the charge carriers, are present inside the semiconductor. And then in this week we moved to considering the situation in which these two separate semiconductors, like a p-type semiconductor and an n-type semiconductor, are brought into a contact with one another to form a junction, a p-n junction. So basically most semiconductor devices contain at least one junction, at least one p-n junction, so to say, between a p-type and n-type semiconductor regions. So semiconductor device characteristics and operation are because of this intimately connected to these p-n junctions. So a considerable amount of attention will be given to the p-n junctions. So in this week, so basically what we did is we considered the zero biased p-n junctions first, and in the subsequent weeks we'll consider the current voltage characteristics of the p-n junction in the next weeks. So what we did was we considered the uniformly doped p-n junction in which one of the region is of the semiconductor is uniformly doped with say acceptor atoms, and the adjacent region, the adjacent layer is uniformly doped with the donor atoms. So we also determined the energy band diagram of a p-n junction inside the thermal equilibrium. We discussed how the space charge region is being created between the p-type and n-type regions. We also applied the Poisson's equation to determine the electric field in the space charge region and also calculated the built-in potential barrier. Okay, so let us consider in this case a step graded, that is an abrupt p-n junction at thermal equilibrium, where the p side doping density is given as Na and the n side doping density given as Nd. So okay, so Np and Nd are the doping densities for p-type for the acceptor and donors respectively, and we see that the value of these concentrations is roughly about 10 to the power 15 to 10 to the power 20 per centimeter cube. Then diffusion of the charge carriers creates the depletion region, which is formed across the junction with width W, and this width is approximately around 1 to 10 micron. Generally we can consider this range, and the depletion region is actually consisting of the region of depletion in the P side plus the region of depletion in the N side. So the total depletion width is summation of the depletion widths in the P type and the N type semiconductor. So at the equilibrium, we can see that the electric field is continuous at the junction. So this particular condition at the equilibrium is satisfied, and a maximum field E max is created, which is exactly at the junction, and a potential difference is also known as the built-in potential, which is formed across the region. So built-in potential, so the E max's value is given by this particular relation. The built-in potential that is generated across the region is given by these equations. This equation I have summarized so that it will be helpful in the problem solving. So the depletion width, which is as a function of the acceptor and the donor concentrations and also the built-in potentials. So this forms the relation for the depletion width, and also the region of depletion in the P side and the N side is also a function of the doping densities, and the sum of these two is nothing but the total depletion width. Then going to the second page for the summary, we also considered a one-sided junction. So for example, consider a stripe graded or say abrupt junction formed by a P and a N plus type of semiconductor, and this is at thermal equilibrium. Where the P type dopant density is Na and the N side dopant density is Nd. So this is a junction. As we can see that the N plus is the region. The plus actually indicates that the doping density in this particular region is way higher than in the adjacent layer, that is in the P layer. So the depletion width on the N side is so small because it has higher concentration of its dopant. We will see in the problems how it comes about, and the total width is approximately equal to the width in the P side, because for the N side it is quite small and we can consider it negligible. So the total width is actually given as the width in the P side. So similarly, if we consider the P plus N type semiconductor, and the P region is highly doped, uh, very highly doped compared to the N side, and in that case the total depletion width is approximated as the width in the N side, because in the P side the depletion width is quite negligible. Also we saw how the width varies as function of built-in potential for the abrupt junction and for the linear graded junction. Okay, so I think with this we can get started with our questions. So this is a common data question. So just a moment, let me see if everything is fine. Yeah. Okay, so this is a common data question for questions number 1 to 3. A silicon PN junction is given at temperature is equal to 300 Kelvin, and it is a zero biased condition, and the doping concentrations given as Na is equal to 2 into 10 to the power 13 per centimeter cube, and Nd is equal to 1 into 10 to the power 16 per centimeter cube. We can use the intrinsic carrier concentration as well as the epsilon for silicon and Kt value is. So the first question using this particular data is as follows: determine the built-in potential voltage which is generated across the junction in volt. So as we saw in the summary, the built-in potential V built-in is given as kT over Q ln of Na times Nd over Ni square. Okay, so we can substitute the value of these parameters, and let me substitute here. Na is given as 2 times 10 to the power 17 times Nd, which is 10 to the power 16, and our intrinsic carrier concentration is 1.5 times 10 to the power 10 its square. So if you just calculate this particular expression, we will get the built-in potential V built-in as equal to 0.772 volt. So the correct answer for this question is this. Okay, did everyone followed it? Any doubt? Okay, I take it as no, and let's move to then the question number 2. So the question number 2 is follows. Determine the width of the depletion region on the n side in micron. So this is actually our case in which a p type and an n type semiconductors are joined to form the p-n junction, and this is the total width of the depletion W, and this is the width in the p side, this is the width in the n side. So this is xp and this is xn. So what we have asked is to calculate the width of the depletion region in the n side. So we need to calculate xn. Okay. Okay, so before that, we know that the value of xn from this formula is that xn depends on the doping concentrations as well as the total width. So let us first calculate the total width, and for that we can use this particular formula. So let us first calculate the total width. So W total width, we can use that formula in which it is 2 times epsilon of silicon times divided by charge with Na plus Nd over Na times Nd times the built-in potential. So we calculated the built-in potential in the last problem, and that is 0.77 volt. So we can substitute all these values here. So let me substitute the value of epsilon for the silicon, that is 11.9 times 8.85 times 10 to the power minus 14 divided by charge in the n side, that is 1.6 times 10 to the power minus 19 coulomb times the concentration in the concentration of acceptors is 2 times 10 to the power 17 plus 1 times 10 to the power 16 the concentration in the doping for the donors, and we can do the multiplication of these here, that is 2 times 10 to the power 31 times the built-in potential that we calculated, which is 0.772. Okay, so if you can just calculate this particular expression, you will get the value of total depletion width, that is W, as 3.26 times 10 to the power minus 5 centimeter. Okay, so as I told you that we can use the formula xn is equal to Na times Na plus Nd multiplied by the total width. So let us do that. xn is equal to Na over Na plus Nd times the total width. Let's just substitute all these values. 2 times 10 to the power 17 divided by 2 times 10 to the power 17 plus 10 to the power 16 divided by the total width that we got, which is 3.26 times 10 to the power minus 5 centimeter. So we will get xn. We can find the value of xn is 3.1 times 10 to the power minus 5 centimeter. So in micron, you can say it is roughly 0.31. Okay, so the depletion width of depletion region on the n side is 0.31 micron. So the answer for this is this here, B. Okay, clear everyone?
Yes, sir.
Okay, so let's move to the question number 3. Okay, so question number 3 is also based on the data given on the first slide. Okay, so the question goes as follows. Determine the magnitude of the maximum electric field at the junction in volt per micrometer. So as also we saw in the summary slide, the maximum electric field that is generated at the junction is given, which is as a function of the depletion width in that particular region and the doping concentrations. So we can write that E max is nothing but Q over epsilon, in our case it is silicon, times the doping times. So in the n side, Nd is the doping concentration, Xn is the width in the n side. So we can substitute the values. We will get 1.6 times 10 to the power minus 19 divided by 11.9 times 10 to the power minus 14 times 8.85 times the doping concentration, that is 1 into 10 to the power 16 per centimeter cube, and the depletion width in the n side in centimeter square we need to put for the consistency. So beware that the units need to be consistent. So for example, we are using xn in centimeter square, this in per centimeter cube, and the units for the epsilon for silicon should be in the centimeter for the length. So if you can just calculate these equation, you will get the value of the maximum electric field generated as 4.72 times 10 to the power plus 4 volt per centimeter. So we want in volt per micron, so we can get it as 4.72 times 1 volt per micrometer. Okay, so the value of the maximum electric field that is found at the exactly at the junction is 4.72 here. Okay, so this is good. Then let us move to the problem number 4. Okay, so the problem number 4 is a little conceptual question. You need to apply a certain level of understanding here. It is quite simple though. Consider a PN junction where there is a difference in the doping on both the sides. Okay, so the doping concentrations on the both sides. If you just consider a PN junction, so this is, if you say it is P type, this is N type, the doping concentration in the P type, which is for the acceptors, is Na, for the donors it is Nd. These two concentrations are different. There is difference in the doping on the both sides. Okay, then the space charge region will be extended more into which region? So So this is the region where the depletion region is formed, and the space charge is actually extended in this particular region. So the question is, so this is the depletion width for the p side, xp. This is the depletion width in the n side, that is xn. So the question is, this particular width, which of the width will be higher considering the difference in the doping? Okay, so this is x is equal to 0, this is for minus xp and plus xn. For this we can apply a simple fact that the product of the doping concentration times the depletion width in that particular region should be equal to the product in the other region, the other side, nd times xn. And this is because the under the equilibrium condition, charge has to be balanced on the either side of the junction. So this particular condition we can use to determine the region in which the space charge region will be more extended into. So let us consider one case in which, let's say a p side, let's say if p side is lightly doped. Okay, so if p side is lightly doped, we can say that the doping concentration of Na is quite less than doping concentration of Nd. Okay, so using this particular relation, we can say that xp, which is equal to Nd over Na times xn. So as we saw that Nd is quite higher than Na, so this ratio is more than 1 here. So we can say that xp is quite higher than xn. So in our case, p side was the lightly doped, and therefore the region in which the space charge region will be highly extended is the p side, because xp is higher and p is lightly doped. So if you consider a difference in the doping, the space charge region will be extended more into the lightly doped region. So going to the next problem, problem number 4. This is also again a common data problem in which this data is given for problem numbers 5 to 7. The problem is as follows. The data in fact is as follows. We consider a step p-n junction made of silicon under zero bias condition for 300 Kelvin temperature, and whose energy band diagram is shown here. We can use these different parameters for the intrinsic carrier concentration, the band gap on the silicon side. So let us go to the question number 5 first. Okay, the 5 is question is, find the doping density on the n side in centimeter per cube, in per centimeter cube. So the doping density is asked. We know that the doping density is given by this equation, n is equal to nc times exponential of minus of ec minus ef by kt. However, we haven't given the value of nc, that is the concentration in the conduction level, so we cannot use this particular formula. So we can also recall one more formula for the doping density, that is n is equal to, in terms of the intrinsic charge carrier concentration, as n is equal to ni times exponential of ef minus ei over kt. So this formula can be used because we have given the intrinsic charge carrier concentration, and we just need to determine the value of ef minus ei. So we need to determine ef minus ei. So we need to determine this particular value. So we can use the fact that the band gap energy is given as 1.12 electron volt. As we know that the band gap is actually the gap between the conduction level and the valence level. So this is Eg given as 1.12 electron volt. So also we know one fact that under the zero bias, the the EFI level is exactly at the middle of the junction. So we know that this particular value is Eg over 2. So we know this value, we can determine EF minus EFI. So EF minus EFI is basically nothing but this difference, that is Eg over 2 minus this difference, that is 0.21 electron volt. Okay, so we can substitute this value here and we can get the doping density on the n side as the charge carrier concentration, intrinsic concentration is given as 1.5 times 10 to the power 10. Then we apply the exponential of the value here. Eg is 1.12, that is, so we can divide by 2, we'll get 0.56 minus 0.21, that is 0.35 electron volt. So we can substitute 0.35 divided by 0.0259 for temperature 300 Kelvin, and we will get the value of doping density and as 1.1 times 10 to the power 16 per centimeter cube. Okay, so let us go to problem number 6, which is also based on the common data. Find the doping density on the p side in centimeter cube. So here we found the doping density in the n side. Now we need to find it on the p side. So for the p side also, we can use by recalling, we can use the similar formula, that is p is equal to ni times exponential of EFI minus EF over kT. Okay, so let us determine EFI minus EF from the band diagram. So we need to determine EFI minus E in the P side. This is P side, this is that. So we need to find this particular value. So again, just applying the band gap values here. So this difference in the intrinsic level and the valence level is half. So it is Eg over 2. And we also know this difference, so we can find out this difference, that is EFI minus EF. So EFI minus EF we can find out, and that comes out to be 0.56 minus 0.18. So we can substitute the value of intrinsic carrier concentration. EFI minus EF comes out to be 0.38 in the P side case. Also substituting the value of kT in the electron volt, 0.0259. So we'll get the doping density on the P side as 3.5 times 10 to the power 16 per centimeter cube. So the answer is D. Okay, so let us move to the next question, the last question for this particular common data. So the 7th question. Okay, so in the 7th question, they have asked us to calculate the built-in potential. So V built-in. So we can just use the formula for built-in potential. If you go to the summary here, the built-in potential as a function of intrinsic charge carrier concentration and the acceptor and donor concentrations is given by this particular relation. So we can use that here and calculate the built-in potential. So let's directly substitute all these values. So V built-in is kT by Q in the electron volt case is 0.0259 times the logarithmic of the charge carrier concentrations Na and Nd. So we calculated in the previous two questions the concentrations in the N side 1.1 times 10 to the power 16 and concentration in the P side, that is 3.5 times 10 to the power 16 per centimeter cube. So you can directly substitute these values. Ten to the power 16 divided by the intrinsic charge carrier concentration squared, so that is 1.5 times 10 to the power 10 whole square. Okay, so this is quite straightforward. If you can just calculate it, you will get the value of built-in potential as 0.729 volt, which is approximately equal to 0.73 volt. Okay, we can also verify our answers by recalling that let me first draw the diagram. Okay, so this difference we have given as 0.21. We can recall that the built-in potential is actually this difference we built in. So we can also verify. Let me first write this value as well, that is 0.18. Okay, so built-in potential from another strategy can be given as this difference, that is this difference minus this difference plus this difference. Sum of these two differences is actually our built-in potential. So this we calculated as the half of the band gap minus 0.18, that is 0.56 minus 0.18 plus this difference, which is half of the band gap minus 0.21. So this comes out to be exactly 0.73 volt. So we can say that our calculated value is actually correct. Okay, so let us go to next question, that is question number 8. Okay, so this question is also similar to the question number 2, in which we determined the depletion width in the particular regions, in which region the space charge region will be more extended. So this question is as follows: consider a N plus P type silicon diode, N plus P junction, in which Wn and Wp we consider Xn and Xp, but let us stick to this notation. These two are the depletion regions on N side and P side respectively, and which of the following relationship is true? Okay, so let me first tell you that N plus P means the plus here signifies that the N side is way highly doped than the P side. So the donor concentration is quite higher than the acceptor concentration here. And we saw that the depletion region, say the space charge region, will be extended more into the lightly doped case. So let me ask you that we know that the P side is lightly doped here. The concentration, the relation is also I have written. So which of the following options you think is the correct option? Can I have at least one answer or two?
P side will be highly. Width of P side will be high.
Yes. So yeah, from this thing we can say that the width on the P side will be higher than width on the N side. The fact that it is way highly doped, we will have this particular notation. So the answer for this question is the width of the P side. Excuse me, do you have any doubt?
It's option C, I said, sir.
Yeah, exactly. So the option C is the correct answer here. So we used the fact that the space charge region will be extended more into the lightly doped side, and in our case the lightly doped side is the P side here. Okay, so shall we move to next question?
Yes, sir.
Okay, so the next question is again a common data question. So consider a step PN junction which is made of a gallium arsenic at 300 Kelvin. At zero bias, only 20% of the total depletion region width is in the P side. So this is important point to remember. The built-in potential is given, V built-in as 1.2 volt. The intrinsic charge carrier concentration and the value of Kt is also given. Also the epsilon for the gallium arsenic semiconductor is given. Choose the closest answer while answering. Okay, so the first question using this common data is as follows. Determine the donor density in the N side in centimeter cube. So we need to find the value of donor density in the N side. So N side, that means the donors, ND is what we have asked to find out. Okay, so the built-in potential is given. So we know a relation of built-in potential with the doping concentrations or donors. So this we have here, so we can use this particular relation, but in this relation we can use the intrinsic charge carrier concentration, and we can use the relation for Na and Nd. So let me go to the question slide. Okay, so the built-in potential as we know is given as Kt over Q ln of acceptors times N and D times Ni squared. Okay, so we need to find out the value of Nd. Ni is given, but we don't know the value of Na. But one piece of information given here is that at zero bias, only 20% of the total depletion region width is in the P side. So XP at the zero bias is 20%, that is 1/5 of the total width. So the remaining width, we know that W is actually the sum of XP plus XN. Okay, so XN is nothing but 4/5 the total width. Okay, so we can write from these two equations that Xn is equal to 4 times XP. Okay, and if you recall the question equation 1 and 5, this equation and equation number 5, we can write Na is equal to 4 times Nd. So the equilibrium condition we have used. So this relationship we can use here to calculate the value of the donors here. So let us solve for ND first. V built in given as 1.2 divided by the value of ET by Q in electron volt. Nine. Okay, so from this we can again solve for value of ND. So we can substitute the value of Ni, that is the intrinsic charge carrier concentration, and we can find the value of ND as 1.15 times 10 to the power 16 per centimeter cube. Okay, similarly we can using this particular relation we can find the concentration of the acceptor. Okay, so let's go to the question number 10, which is based on this piece of information. Determine the depletion region width in micrometers. So we need to find the total depletion width W. Okay, so for W we know the relation that is function of the carrier concentrations. This particular function, which is this particular relation, which is the function of the doping concentrations in the concentrations of acceptors and donors, and also the built-in potential. So we have all those parameters required, so we can just substitute to find out the total depletion width. Let me just substitute it for you. So I have substituted the value of epsilon divided by the charge I also use the relation between ND and Na times the built-in potential. Okay, so if we just calculate it, you will get the depletion width as 4.31 times 10 to the power minus 5 centimeter. So we need it in micron, so we can rearrange it to 0.31 micron. So the total depletion width is 0.431 micrometer, approximately 0.43 micron. Okay, let us go to the last question based on this data, that is question number 11. Question number 11 is as follows: determine the maximum electric field in kilovolt per centimeter. Again, just recalling the formula from the recap slide, the maximum electric field which is generated at the junction, middle of the junction, is given, which is as a function of the doping concentrations, the epsilon, and the width in that particular region. So we can use that relation here to find out the maximum electric field generated, that is E max. Q, or in our case it is gallium arsenide times Xn times. So let us consider the N side. You can similarly go to the P side case and you can get the same result. For the silicon case, epsilon is given as 12.88 times 8.85 times 10 to the power minus 14. Xn is 4/5 of the total width, that is 4.31 times 10 to the power minus 5. Times Nd, that is 1.15 times 10 to the power 16. So here we used that Xn is 4/5 W. Okay, so this is just a simple calculation. We can get the value of maximum electric field as 5.57 times 10 to the power 4 volt per centimeter, and we need to find out in the kilovolt, so we will just multiply it by 10 to the power minus 3, so we'll get it as 55.7 volt kilovolt per centimeter. Okay, so the maximum electric field developed across the junction in kilovolt per centimeter is 55.7. So the closest answer here is 55.6. Okay, is it clear, everyone? Any doubt here?
Yes, sir.
Okay, so this brings us to the last question for today's session. The question is, so this question I have taken from previous year's GATE question paper. So it appeared in the EC GATE 2016, and the question is quite intriguing question. Okay, consider a silicon PN junction with a uniform acceptor doping concentration of 10 to the power 17 per centimeter cube on the P side and a uniform donor doping concentration of 10 to the power 16 per centimeter cube on N side. No external voltage is applied to the diode, so the zero bias condition is prevalent. We also need to use the intrinsic array concentration given here, the epsilon for silicon here, and the magnitude of charge per unit junction area is asked. So the magnitude of charge per unit area in nanocoulomb per centimeter cube in the depletion region on the P side is. So this is the question. So again, we can use the charge neutrality condition. So charge neutrality condition is that the charge of donors is equal to the charge of acceptors. So charge of donors we can recall from the equation number 1. This particular equilibrium condition we have used. The charge in the donors is equal to charge in the acceptors region. So we can write it as okay. So the charge on the P side is this, which is for the acceptors, and this is for the donors. Okay, so we need to find out the charge, this particular value. So for that we need to find out the XP. Na is given, charge we know, XP we need to find out, and for that we know that XP is given as Nd over Na plus Nd times the total width. You can recall from equation number 3 or 4 from the summary slides. The Nd and Na are given. So if you use these values 10 to the power 16 and 10 to the power 17 here, so we can write it as 10 over 11. of the total width. Let us consider this is 1. So first let us find out the value of total depletion width. From that we can get the value of depletion width in the p side, and if we substitute that value here, we will get the total charge in the p side. So the magnitude of the charge per unit area in the depletion region on the p side we can get. So let us find out the value of W first. We can use simple relation for W as 2 times epsilon for silicon divided by the charge times Na plus Nd over Na times Nd multiplied by the built-in potential. The built-in potential is okay, so we can find out this particular value of W if you just substitute all these values. I'll skip the substitution, and the value of W we can get, but for that VBI is also not given. So the built-in potential need to be determined first. So we know that the built-in potential is given as KT over Q ln of Na times Nd over Ni square. So we can find the built-in potential, and we can get the value of built-in potential as 0.754 volt. If you substitute the value of built-in potential in equation number 2 for the total depletion width, you will get W is equal to 3.3 times 10 to the power minus 5 centimeter. Okay, so now we have W that is the total depletion width. We also have the acceptor concentration and the charge. So we can find the value of Q based on using XP value from equation 1. So Q acceptors is 1.6 times 10 to the power minus 19, that is the value of Q, times the value of Na, that is 10 to the power 17, times the value of Xp, that is 10 over 11, times W, that is 3.3 times 10 to the power minus 5. Okay, so if you just calculate it, you will get this value as 4.82 times 10 to the power minus 7 coulomb per centimeter square. Now we need to determine it in the nanocoulomb per centimeter square. So just rearranging, you will get it as 482 nanocoulomb per centimeter cube. So approximately in the assignment, you will have the option 500 nanocoulomb per centimeter square as the correct answer. Okay, is this clear? Any doubt in this problem? Anybody? Do you have any doubt? Okay.
No, sir.
Okay. So I consider as no, and so this brings me to the last slide, that is a thank you slide.
So one question.
Yeah, sure. Tell me.
So what is the unit of charge density, sir? So rho coulomb per centimeter, coulomb per meter square, or coulomb per meter cube, sir. In when we calculate the depletion region, there we assume that the rho to be coulomb per centimeter cube, right? That's what usually it is coulomb per meter square, right, sir? Density in the sense.
Yeah.
But in the lectures, it's given as coulomb per centimeter cube.
Charge density.
Yeah, rho.
Okay, and you are saying that charge density should be coulomb per meter squared.
Yeah. You can change to coulomb per centimeter square also, that's not problem. But in lectures, it's said as coulomb per centimeter cube or meter cube. How? That's what my question.
Because we are considering a bulk semiconductor here, because in bulk, so three side if you can consider, it is volume. So charge per volume is considered. In your case, you are saying charge per area. So that density is different.
Yeah.
That is surface charge density. What is expressed in the lectures is the volume charge density.
Okay.
So that's the
Okay.
difference. So the surface charge density will have centimeter square or meter square in the denominator, and the volume charge density that is
Volume charge.
will have volume unit, that is centimeter cube or meter cube.
Okay.
Is it clear?
Yes.
Okay. So okay. So thank you everyone for joining for the fourth live session, and I hope to see you in the fifth live session, that is on August 26th at 6 p.m. Indian Standard Time. So meanwhile, you can again go back and refer to the recordings that I'll upload on my YouTube channel. So you can find a playlist there, that NPTEL-ISD live sessions 2022. So you can refer to questions if you could not get anything in the live session. You can also ask question there in the comments, or there is a dedicated discussion forum in the NPTEL course site, so you can go there and also create open your discussion question, so the regular TAs or in fact professors, Professor Imani can also reply there, and if it is related to the live session I can also reply. So feel free to ask questions in different forums and different platforms that are available to you, so that this particular course will be more fruitful to you. So again, thank you so much for joining, and I hope to see you in the next live session. Thank you.
Thank you, sir.
Thank you. You're welcome.
Thank you, sir.
Okay, so thank you everyone again for joining for this live session, and I hope to see you all in the next live session, that is live session number 5 for week 5, scheduled on the 26th August at 6 p.m. Indian Standard Time. Till then, bye bye and have a nice weekend. Thank you.